science. And we are going to move on to the next major topic. But before we do, I have this amazing pen, so I'm just going to So some of you might remember that I said that this module has a little bit of multiple personality disorder, a little bit of schizophrenia, because we have these three major subtopics: information visualization, volume visualization, and flow visualization. And that's not typical. Usually you take a class in information visualization only, or scientific visualization only, or possibly volume visualization only, or flow visualization only, and not this mixture. So we're switching gears into volume visualization, and you'll see that it's different. It's got a different look and feel, and there are some reasons for that we will discuss as we go along. So we're just this is gonna be just a general overview and introduction to this topic of volume visualization, similar to the introduction you had with information visualization. So in the first part, the first 6 or so lectures, we focused on basically information visualization, which was abstract data, and the data had no inherent spatial geometry, generally speaking. Although with the Project Tycho data, that's really, you can include space in that data, and that's geospace. That's a flat 2D surface. It's a map projection. Here we're talking about volume data, so data that occupies a 3D volume. So X, Y, and Z. So the data occupies a 3D volume, but what we actually see is projected onto a 2D image plane or a 2D screen. And the volume visualization can be summarized in one sentence, really. How do you take the 3D volume and project it onto a 2D image? That's what the study of volume visualization is. It's how do you take three-dimensional or a cube, you could say a cube of data, and project it onto a 2D image. That's what we're going to study. We're going to study the different ways that can happen, because it's non-trivial. It's tricky. You have different things you have to think about. Like, what about occlusion? What about depth? What about some data hiding behind other data? What about the massive amount? Right? It's a big amount, so it's a tricky business. So it's generally a 3D array of scalar data. So it's 1D in the sense that it's usually just a set of scalars. Right? It's not n-dimensional necessarily, like we said in information visualization. And it's usually dense. And we have to consider like what the user is interested in again as well, or focus in context. So the reason the look and feel of volume visualization is so much different than info-based is because of where the data often comes from. So you've all had personal experiences with volume visualization. How many people here have had an X-ray before? That is a very standard example. So your X-ray is your skeletal information. It's three-dimensional, by the way. It's 3D. But it's projected onto a 2D film. using a very special technology. And that's what makes it so different, because that data came from a very expensive piece of equipment. It's very specialized. It has a very special focus, the purpose. It's very expensive, specialized equipment. The operators need to be trained to use the equipment. And the people that look at the x-rays, the doctors, also need many years of training before they can correctly interpret the x-rays. So the sources of volume visualization data generally come from specialists, generally speaking. So in information visualization, you just Google like data sets and you just get bazillions of endless data sets. But with volume visualization, it's not quite the same. The data sets come from more specialized sources, like medicine, engineering. Anybody here have any exposure to engineering at all? Like even friends like studying engineering? Good, good. So a lot of this data comes from engineering, and we are going to talk about that in this module, by the way. But again, that's kind of a special profession, right? It's not the general populace. The general populace generates InfoVis data, whereas usually, not always, there are exceptions to everything, the specialists generate the volume visualization data. And in InfoVis, the data is not necessarily organized according to any special spatial structure. Right? Every InfoVis data set has its own format and structure that's special to that data set. But volume visualization data is usually, not always, structured on a three-dimensional Cartesian grid. Right? dx means the space between data samples along the x-axis. dy is the space between data samples along the y-axis. And then dz is generally the space between data samples in the z, or the depth direction. So usually the data is uniform resolution in the xy plane, and then there's some enhancement stage or pre-processing stage that makes it uniform along the z direction. For example, 512 cubed. The data could be on a 512 cubed grid, which ends up being a lot of data. And how we interpret that data, what we do, how we process it affects the algorithms that we use and so on. Sometimes data is not on a structured grid, on a nice Cartesian grid. It could be on a curvilinear grid or an unstructured grid even. And in this case, the data are not a set of cubes or voxels, but tetrahedra. Tetrahedron, in case anybody forgot, is a 3D primary cell that is the simplex with 4 triangular faces, 6 edges, and 4 vertices. It's a funny description. But think of a pyramid. That's like what it looks like. I really should have an image, a picture on there of a tetrahedron. Yeah. Anybody know what a voxel is already? Would you say Maurice? No. Marcelli. A vertical. That is correct. A volumetric pixel. Volumetric pixel is one way of saying. You can also say volume element. A pixel, everybody knows what a pixel is? Who wants to say what a pixel is or what that word? You should know what a pixel is because you stare at them all day, every day. Anybody feeling brave? No, nobody's feeling brave. Picture element, that's what a pixel is. That is serious pub quiz knowledge. You need to know that. Pixel. But we're going to talk about voxel here, which is a 3D pixel or a volume element. So the challenges in volume visualization is we have a lot of data samples. So imagine 512 cubed. Anybody know what that number is? That's in the millions, 512 cubed. It's like 2.5 million or something like that. Oh, here it is. 512 megabytes could be a typical volume viz data set. This is 512 by 512 by 1024. At 16 bits per voxel. So a very typical data set size is 512 megabytes, which is still like big. It's still big. And how do you look at 512 megabytes worth of data fast? For example, at 5 frames a second or 10 frames a second. How do you look at it? Very quickly, and which subsets do you choose to look at? Because you cannot look at the whole thing at the same time. You must choose some subsets. You have no choice. Yeah. Because otherwise you can't see anything. These are 2 different ways to look at the same set of data, the same set of 3D Cartesian grid data. Actually, I'm going to start with the cell. This is how we would probably normally think of volume data, structuring it on some sort of a grid. So this is a cube, and in the cube, the data samples are stored at the corners of the cube, and they're connected by edges. That's a cell, and I think that's what we would all think of. If I said, please come up with a spatial arrangement for volume data, I think this is what everybody would come up with. And then to get any values inside the cell or along the edges, interpolation is used. Somebody already mentioned interpolation. I forgot. Was it you? Yeah. Another way to view the same data is as a voxel, where the data is stored at the center of the cubes. So it's just shifting the cube along x a half a unit, along y a half a unit, and along z a half a unit. So it's like rearranging the edges. And the data is not always interpolated. So some algorithms that we go over look at the data in terms of cells, process the data on a cell-by-cell basis, and some algorithms that we look at process the data on a voxel-by-voxel basis. They interpret the data as a set of voxels. And so some new terminology. There's always kind of a lot of new terminology in these introductions to topics. But before I go on, I thought it would be fun to just show a little demo. Like a nice example demo of some volume visualization. What do you guys think? Would that be cool? So what does it look like? What does volume visualization even look like? Here's a little demo. I'm not going to explain the demo in detail. It just gives you some idea of what it is we're talking about and what does it look like. What does volume visualization look like in practice, so to speak? So this is a combination of virtual reality and volume visualization together. This is, everybody hopefully can recognize that. But it's a medical data set. Right? So we see a person's skin, and it's a volume visualization data set. The data is arranged on a 3D Cartesian grid, but we don't see all the data samples at the same time. The user has chosen a subset of the data. In this case, it's the skin-ish, and is now interacting with the volume data in this virtual reality environment. So they moved the light source. Now they're practicing selection in 3D. That's a challenging task. I'm sure some of you have wondered about that already. They have a virtual clipboard that they're interacting with in the virtual world. Right? They've changed the subset of the data. Now we're no longer focusing on skin, but we're focusing on the bones. And they're taking that selection object and then rotating the volume around. And now they're going to filter, they're changing the subset again of the data to visualize. So in this case it is the skin, back to the skin. Anybody know what that object is behind the head? There's some other object behind the head. Anybody have any ideas?
Hello.
A pillow? Yes, that's close. It's the bench that you use to carry a cadaver, right? So that person is actually laying down on a bench, and that's the thing that, or whatever that's the object that the head is laying down on. So that's when you turn on semi-transparency, so you add some semi-transparency to the volume so you can see through it, just a little bit like an X-ray. This is adding color, selecting subsets of the data and adding color, right? We can assign different colors and opacities to different subsets of the data. For example, the bones, soft tissue, different subsets of soft tissue like kidneys and respiratory systems. This is a clipping plane applied, or a clipping cube rather, applied to the volume. So that's looking inside using a clipping volume and interacting with a clipping volume. You can see the real person here. It's not very, well, it is pretty obvious, right? That's a real person. It's easier to see on my screen than it is on the projection. And that's the user selecting objects in 3D. I'm sure that some of you have wondered about that, like how do you select objects and interact with objects in 3D, not just 2D. It's a challenging problem, actually. So that's the user selecting kidneys, for example, with their virtual clipboard. They have a real board in their hand, and then they have a virtual clipboard in the scene. And they're using the virtual clipboard to see inside the volume. And those are the kidneys that you're seeing, the red objects, the red soft tissue. So now we're interacting with the volume with two hands, so to speak, left and right-handed interaction. And this is a time-dependent volume visualization. So we didn't mention that yet, but this is the volume changing over time. Anybody know what that is? It's a human heart, that's right. That's right. So that's a human heart beating, and the same interaction techniques being applied to the time-dependent volume visualization. And if you're interested in this, you can see a copy of this video on YouTube, on the DataViz YouTube channel. Because I was very, very interested when I first saw this. In fact, I was shocked when I first saw it, actually. I was really surprised. I had never seen anything like that before. And I still remember seeing the beating heart for the first time, and I was really, really surprised. So that's what we're talking about, all this stuff about data being on a three-dimensional grid and all the terminology. That's an example of volume visualization. And We're going to introduce a lot of new terms and a lot of new terminology. And interpolation is one of those terms that we're going to use all the time. And what does it mean? To estimate a value of a function at a point P given known function values and points that bracket P. That's one definition. I'll try to bring like that down to earth, so to speak. What do you do every day? You turn on the news and you look at the weather, right? You want to know, is it going to be sunny? Can I go to the beach tomorrow, or am I going to go to the movies? Or is it going to rain? And every day you look at a map of the UK and you see a weather forecast. Now the images that you see are smooth images. They're smooth. So if you go to like Neath or Port Talbot, and you want to know what the weather forecast there is, you still get a weather forecast. But there might not be any data directly from Neath or Port Talbot. Anybody know where the weather data comes from? Anybody ever wonder about that? It comes from weather stations. So stations that measure things like temperature, pressure, wind direction, and lots of other things that I don't even know about. You can see one on Kilvey Hill. Anybody go up Kilvey Hill? But those weather stations are not everywhere, are they? You cannot build a weather station everywhere because it's too expensive. You can build a finite number of those weather stations to measure the temperature and the pressure, barometric pressure, and wind speed and direction at different locations throughout the UK. But when you look at the weather report, do you see the weather stations? No, you don't see any weather stations when you look at the weather report or the forecast. You just see a smooth, nice map like that shows the temperature everywhere in the UK. It doesn't matter where you're looking. So what has happened is the meteorologist or the Met Office has taken the readings from all of the weather stations spread across the UK, taken that data and then interpolated it to get complete coverage of the UK, filling in the missing values between the weather stations. That's interpolating the data. So filling in those missing values between the measured values. So there's a weather station in Swansea, there's probably one in Cardiff, but we're not going to have a weather station in Neath and Port Talbot. Well, maybe there are. Anybody from Neath or Port Talbot here? But you're not going to have a lot of weather stations between Swansea and Neath. But you'll still always know the temperature. And the weather forecast presents a very smooth picture of the temperature using interpolation. So the idea is that if I have a value here at this point, and I have another value at this point, and I want to derive a value between the 2 points, I can do that in different ways of interpolating. One is called nearest neighbor interpolation. So I just copy the value, I find the value of my nearest neighbor. So at this point P, I have a distance d away from F1 and a distance d minus d away from F2. D is the total distance between F2 and F1, and small d is the distance between P and F1. If small d is less than uppercase D, then my nearest neighbor is F1, and I just use F1's value. That's also called nearest neighbor interpolation. So if I'm in Neath and I want the temperature, a temperature, to report a temperature for the weather forecast, and I don't have a weather station, I use Swansea's weather station temperature, not Cardiff's, because Neath is closer to Cardiff. I'm sorry, Neath is closer to Swansea than Cardiff. So I just copy Swansea's weather forecast. That is the least accurate form of interpolation, but it's also the fastest. It takes the least computation time. Another one is called linear interpolation, and I think you guys have heard of that before from computer graphics. Wasn't that a topic in computer graphics? Linear interpolation, so you get to see it again from a database viewpoint. And that's when we take into account the value at both sides of the unknown, on both sides of the unknown. And we take into account the distance we are from both sides. So the closer P is to F1, the more influence F1 has on the final result. And vice versa, the further away F2 is from P, the less influence F2 has on P in terms of value. So we compute two coefficients called influence. You could call them influences if you want, but the percentage of distance away from the neighboring points. So the formula for linear interpolation is summing up F1 divided by D, uppercase D minus lowercase d divided by d, so that's the normalization. And you can see as d minus d increases, the influence of F1 increases. And as lowercase d decreases, the influence of F2 also increases. So let's put in some actual numbers. So here's my original configuration. And if I use nearest neighbor, here's putting in actual numbers. So for example, I have 100 degrees Celsius, and it's not a very realistic example, in Swansea, and 200 degrees Celsius in Cardiff. And I want to find out what my temperature is in Neath. I'm pretty close to Swansea, so I just plug in the numbers into my formula. 10 is the total distance between Swansea and Cardiff. 10 minus 2 is 8. 8 divided by 10 is 0.8. So the influence of Swansea is 80%. I take 80% of the value from Swansea, and I add it to 2 over 10, which is 20% of the value from Cardiff. I add 80% from Swansea to 20% from Cardiff, and I get my sum 100% and a resulting temperature. In this case, it's 120 degrees. That's just one example of linear interpolation. So you can see as that point slides back and forth, if we could slide back this point back and forth, that would be a fun exercise. Maybe there's a web page that does that already. The closer I get to Swansea, the closer it's going to get to 100 degrees. The closer I get to Cardiff, the closer it's going to turn into 200 degrees. Everybody confused? Hopefully. Anyway, it will click, like it's not very difficult. We use the word interpolation a lot in volume visualization and flow visualization. And we don't usually use it that much in information visualization. It's more of a sci-viz term. Anybody know why? That's a difficult question. Name?
Dan,
Dan.
and the data points in information visualization are usually discrete, aren't they? So it's like
Exactly. So in information visualization, we're representing abstract things that don't necessarily have a correspondence in nature. They do sometimes, but not necessarily. In scientific visualization, we're usually representing something that occurs in nature. And nature produces smooth objects, at least based on our perceptions of the world. The objects are smooth. And therefore, we need linear interpolation to create a smooth data set that represents nature somehow. When we measure something, we take discrete samples. That's a representation, but we want to reconstruct the underlying behavior or object, usually using interpolation, because it's too difficult. You can't store all the data in the world. That's what trilinear, this one's called linear interpolation, this one is called trilinear interpolation, and that's, we need trilinear interpolation to get the values inside of a cube. And this is the formula for trilinear interpolation. It's complicated, and you'll be asked to memorize that formula for the test. You have to know that, like, inside and out on the test. That formula. No, you don't, actually. You don't. Nobody laughed. Except for me. We will talk more about that. We will keep, that will be a recurring theme. Here's what it looks like in computer graphics. This is something you've all seen before. Well, all the third year students, because I think you all took a computer graphics class. If we want to generate images of things like spheres, this is the influence of different kinds of interpolation. Here's a sphere rendered using nearest neighbor interpolation. And we see this kind of aliasing, it's called an aliasing artifact. And here's a sphere generated using linear interpolation, which results in smoother edges. Any questions so far? We will stop there then, and I look forward to seeing you all again at 1700 hours.